Okay. So the standard integrals that are involved with quadratic denominators. We have these two, a squared minus x squared minus a squared, which could be factorised, difference of two squares. You would then perform partial fractions on it. When you do it, I tend to just memorise these, because I don't think they're too hard to remember. The next ones which have quadratic denominators are our inverse trig ones. We know a squared plus x squared, but then we have square root of a squared minus x squared. But then there's another two which we haven't used yet, and there you go. Those are also similar to each other. They're both logs, x plus whatever the surd is in the fraction. So you'll notice the top one, the surd is x squared minus a squared. That's what's in the log, x squared minus a squared. The bottom one is a squared plus x squared, so that's what's in the surd in the log, a squared plus x squared. So essentially they're sort of like the same, but it's just that whatever's in the surd, that's what goes in the log. Let's do some examples. So I get something like this: 5 dx on x squared plus 4x plus 9. Now of course you could try and factorise it. Multiplies together give 9, adds together give 4. Doesn't work, does it? There's nothing nice that works there. So what we do is we complete the square on the bottom. And that gets us in the form of x squared plus a squared. But instead of x, we've got x plus 2. So it's just a shift in the curve. So that's all right. My standard integral for dx on x squared plus a squared, that's the inverse tan one. So it'll be 1 over a, or in this case, we've got 5 lots of it, so it'll be 5 over a. A in this case is the square root of 5. Inverse tan x over a. So we have 5 lots of 1 over the square root of 5, inverse tan x plus 2 on the square root of 5. 5 and the square root of 5 cancel, giving me root 5 inverse tan x plus 2 on root 5. Okay. Now, square root of x squared minus 4x plus 1. The standard integrals all have constants in the top. So what we have to do with this one is split it into two integrals. So the very first thing I do, okay, when I'm setting this up, the first fraction, I simply create the derivative of what's in the surd, or whatever's in the denominator, whether it be a surd or not, it doesn't matter. But the quadratic is what's important. So I create the derivative of the quadratic in the denominator. X squared minus 4x plus 1, its derivative is 2x minus 4. But I don't have 2x, I've got 3x, so I need to balance that out. That gives me 3 on 2 out the front, because 3 on 2 times 2x would give me the 3x that I want. Now I just have to work out what has happened with the constant now, because the negative 4 times 3 on 2 is not going to give me plus 2. Negative 4 times 3 on 2 actually gives me negative 6. So therefore my constant in the second integral, I have to add 8, so it becomes plus 8. Now what that means is the first integral becomes a very nice standard integral. It's just du on root u, so that's why I deliberately made the derivative on top. So I've got du on root u, which I know integrates to be 2 root u. The second one, I can complete the square and come up with a standard integral. So the first one, if you don't see the du on root u straight away, well, do a substitution. And you'll get du on root u. The second one, completing the square, x minus 2 all squared, but then it'll be minus 3. So it's in the form of the square root of x squared minus a squared, which is, that was our log ones, that was one of the last two, wasn't it? So that'll become the log of x minus 2 in this case, not x, but then plus the surd. So the du on root u became 2 root u. And, well, it's 8 on the top of the fraction, so 8 log. Now the standard integral was x plus the surd. Well, instead of x, we've got x minus 2. So we'll have x minus 2 plus the surd. Notice I didn't write it in the completing the square form. I went back to the actual quadratic itself, x squared minus 4x plus 1. I just got to fix up my root u and substitute back in. There it is. So 3 root x squared minus 4x plus 1 out the front. So when we have a linear function on top of the quadratic, we want to create the derivative on top, the first one. So I'll either end up with du on root u if it's got a square root, or if it doesn't have a square root, I'll just have du on u, which will be log u. So it'll always be one of those two things. And the second one will become one of those standard integrals. Now, you might be looking at this and thinking, hang on, there's no quadratic. But there will become one. What we're going to do here, instead of rationalising the denominator, I'm going to rationalise the numerator. And when I do that, I get a question like the last one, where I've got a linear function on the square root of a quadratic. So I'm going to split that into two integrals. The first one, I want the derivative on top. Now, the derivative of 6 minus x squared is minus 2x minus 1. I want plus x, so I'll multiply by minus a half. Now I've got to work out what I've done with my constant. Minus a half times minus 1 would be positive a half. I want to get to 3. So to get from positive half to 3, I've got to add 2.5 or 5 on 2. Now I don't know why I put the 5 in the integral and the 2 outside the integral. I mean, you could have just as easily had 5 on 2 out the front of that integral. It doesn't really matter. But now, the first one, again, du on root u, so that's going to become 2 root u. The second one, I'm going to have to complete the square on. But once again, if you don't notice that du on root u, we'll just do a substitution. U equals 6 minus x squared. But there it is, du on root u. Completing the square on the second one. We've got to be real careful here, because notice it's minus x squared. So the first thing I always do with these is I actually write minus parentheses squared, and I put the x in, so I know it's going to be minus x squared. Now when I expand out, I want minus x. So half the coefficient of x is negative a half, but remember when I expand out, I want minus, and it's minus the whole fraction, so I need a plus inside to end up with minus x when I expand that all out. Be real careful with those negatives. Make sure, double check, expand out if you have to, but make sure you got the right sign there. And we'll have a half squared. So half squared is a quarter, but it's negative a half. I want to get to 6, so I have to add 25 on 4. So a in this case is 5 on 2. It's in the form of the square root of a squared minus x squared, which is inverse sine. It'll be an inverse sine. So there we go. Yes, sure indeed, the first one turned to 2 root u, and the second one inverse sine of 2x plus a half on 5. Let's make that look neater. That's a bit better. So we substituted in for the u and tidied up the fraction inside the inverse sine function. So the missing standard integrals, the ones that aren't there. So dx on a squared minus x squared is 1 on 2a, that'll give a plus x, a minus x. So when the integrand, by the way, in case you didn't know, the integrand is what you integrate. So the function after the integral symbol is the integrand. So the integrand finishes with x, so I know the primitive finishes with a minus x. And dx on x squared minus a squared, the integrand begins with x, so the primitive begins with x minus a. So that's just how my weird mind works. However you come up with, whichever way to memorise it, that's up to you, I suppose. Otherwise, you're going to have to do partial fractions on it each time. That's just going to save time if you know the integral. Alright, well, big handfuls of questions there.